Yeah, unfortunately they don't let you take out all of the pages you don't want. You kind of have to do by chapter, but it was still better than having to buy the whole book. So I think we left off on pH last time in chapter 3. I know we were close to done with it. You guys getting cold? I think it's ventilated out. We can probably close that door. Thank you. Chapter 2. We're going to do chapter 3 in class tomorrow. So it'll probably be the following week that I'll have it be due. Give you time to work on it. Tomorrow. The class is Tuesday, Wednesday. Okay, so we left off on pH. So the pH is going to be important in biology. When we look at the pH, it's going to tell you whether or not something is an acid or a base. And there's a couple different ways that they are defined, but one of them is based on the amount of hydrogen ions that are available in there is one of the more common definitions for it. The hydrogen ion is going to shift the water what happens is there's a shift in the water molecules and one of the hydrogen atoms leaves and it doesn't take its electrons with it, so it's going to be positively charged, and that's your hydrogen ion. When you split up water, there's no way of splitting it equally in half because you've got one oxygen and two hydrogens. So you can't split the oxygen in half and still have it be oxygen. So the oxygen is going to have to go with one of these or the other. So we'll say it chooses to go here. Those two bonds there that are for this shared bonds between the hydrogen and the water, this pair is more electronegative than the hydrogen is. Remember, hydrogen's way on the other side of the chart. It's just going to give up those electrons in there. So that's why you get one with a positive charge, and the hydroxide is going to have the negative charge because it has the extra electron with it in there. So the hydronium is when this proton hooks onto another water, and then you have three hydrogens in there with a plus. Usually when they talk about acids, they'll represent it with an H plus in there. Even though it does form the hydronium in there, no one talks about it as hydronium. We just talk about it being the hydrogen ion in there. So if you see that, that's why you're seeing that in there. The convention is just to represent it as hydrogen ion. The reaction of these coming apart and going back together to be water is reversible. So you're going to have it going back and forth where they'll be attached and come apart all the time until it reaches a state of equilibrium. When it reaches the equilibrium, it doesn't mean it's not going back and forth being apart and separated anymore. It just means the same number of them are coming together as are separating, so that your net number apart and your net number that are together remain constant in there. So in pure water, what you have is one molecule in every 544 million is dissociated. So your concentration of each ion in pure water is 10 to the negative 7th molarity at 25 degrees Celsius, which comes out to be a pH of 7. What the pH represents is the negative log of this number here. So that's where the 7 comes from in there. And the reason we care about pH is both the hydroxide ion and the hydrogen ion are very reactive, and they can drastically affect other molecules in there. So this is a pH scale in here. It goes from 0 to 14. And this here shows you that when you've got an acidic solution, you've got more free hydrogen ions in there. Neutral Everything is equal concentration. When you've got a basic solution in there, you've got more free hydroxides in there. So 7 is neutral, it's your pure water here. So your blood, sweat, tears are pretty close to around pH 7. Saliva is a little more acidic, urine a little more acidic in there. A lot of times people get this impression that, ooh, acids are bad, and they're not bad. You just need to have the right pH in the right place. In your stomach, you want to have this really acidic condition in there. If you don't, you're not going to digest your food in there. You're not going to absorb calcium without that acid in there. And then we don't have a lot of places that are strongly basic in the body. But a lot of times people will get really freaked out about battery acid. It's just if you've got a battery that's leaking something on there, most people are like, ah, get it away from me, take it to the garbage like that. And maybe you've had the experience where you're taking batteries out of something and you don't even realize that that battery's leaking. Was your hand burned off? No, you didn't even feel the stuff on there. Now, no, it's not good to leave it on your skin long term, but when you look, there's other things that, do you get really upset about juicing a lemon with your hand? No. In there. Do you get upset about pouring this stuff down your throat? No. Those are really acidic in there. And so that idea that really acidic stuff is bad is just something that people have kind of come up with from wives' tales on things. If you have an acid environment, you want to have acid things in there in the body. Now, if you put lemon juice in your bloodstream, that's going to be bad in there. So, likewise, things that are really basic are not really bad either. However, these things can be just as damaging to the body if they get in the wrong spot. So you can have a burn from a strong base on the skin just like you could have a burn from a strong acid on the skin. So effects of changes in pH. When an acid dissolves in water, it's going to donate additional hydrogen ions in there. So the acids increase that hydrogen concentration, the hydrogen ion concentration. The bases are going to reduce the hydrogen ion in the solution in there, so sometimes you're going to see it being represented as more hydroxides in there because you've reduced the hydrogens that were attached to them in there, or indirectly forming the hydroxide ions. So with hydrogen chloride, when that gets put in water, you'll have it separate the hydrogen chloride in there. This will bind up with other things in there, leaving more of the hydrogen ion in there. And then sodium hydroxide will form a base in water in there. So when we talk about something being a weak or strong acid or base, it's not the pH that's going to determine is it weak or strong. It determines does it completely dissociate in water, in which case you represent it with a one-way arrow, and that's a strong acid or base. A weak one does not completely dissociate, so the reaction is more reversible in there, and you have a fixed ratio at equilibrium, but the reaction reverses more equally in there. So that's one of the things that sometimes is kind of confusing to people, is it's about the strength of the bond, not the pH when we talk about a strong acid or a weak acid. So your pH scale in there is calculated in an aqueous solution at 25 degrees Celsius. It's the product of the concentration of the hydrogen ions and the hydroxides. You're not going to have to calculate this out in here. I'll save this fun for you in chemistry. But basically, you've got that concentration of the hydrogen ions at 10 to the negative 7th, the hydroxides 10 to the negative 7th. So when you multiply those, it comes out to be 10 to the negative 14. That's why the pH scale is 0 to 14. So there is a mathematical reason behind it. So if you were to increase the hydrogen ion in there, the concentration 10 to the negative 5th. 10 to the negative 5th is a bigger number than 10 to the negative 7, because remember when you're looking at using those exponents in there, that's how many zeros you have beforehand. So that's why it's making it a bigger number. When you multiply it by the negative log in there, that makes it pH 5. So that's why pH 5 is more acidic and has more hydrogen ions in it, is because of the negative log. So this is the equation that they use. It's the negative log 10 to the 7th. So you come out and you do negative times negative gives you a positive, and that's where the pH is in there. So in here, I've never had to calculate the pH of a solution for anything outside of a chemistry class. So we're not going, you can see there is a mathematical reason behind it in there. And this is one of those things where I'm going to say to you, for a biology class, you can go, oh yeah, there's a reason behind it. Just accept it and move on in there. You'll get to do the math later on with somebody else who enjoys that kind of math. So a buffer is going to be a substance that's going to help to minimize the pH change. It's going to soften the change in there. One of the reasons we care about buffers in biology is a lot of times a pH change is going to be what turns something on and off. So if you want to turn on digestion and turn it off, you don't want that getting turned on and off at the wrong time or too easily in there. So this would be kind of like if you have a light switch and it goes on and off, there's a little bit of tension in that light switch. Or if you have the lock on a door where it goes up and down like on a sliding glass door. And if it doesn't have that tension in there, when you push it down, it locks the door. This can be a problem. And I actually experienced this where I had one of those that did not have enough tension in it. So if there's not enough tension, it could just fall too easily. Then what happens? Your door is locked when you don't want it to be. And that happened to me with my sliding glass door. Twice in one day I went out in the yard, and all it took was the dog jumping up on the door and me locked outside when I don't want to be. So the pH just makes it so that the buffer makes it so your pH change doesn't go too quickly. It helps to absorb some of those extra ions in there. Other places where acid is important, when we talk about acid precipitation, so they call it precipitation. We tend to think of it as rain here because that's the majority of our precipitation in Washington. But if you live someplace where you get lots of fog or snow, that can be acidic as well. And it's defined as having a pH less than 5.2. A lot of what causes it is burning the fossil fuels. It's going to release the sulfur oxides and nitrous oxides into the air that are going to interact with the water just like they would cause an acid. If you were to do it in a chemistry lab, they'll do the same thing with the precipitation in the air. Also with the carbon dioxide, that gets absorbed by the oceans and it will react with the seawater to form carbonic acid. And that dissociates to make bicarbonate and carbonate in there. And it's going to change the solubility of some of the corals and other organisms in there. So just like if you were to take one of your teeth and you put it out and you put it in some acid, it's going to change the solubility of the calcium salts in your teeth. You can do it with an egg shell where you put it, you've probably seen some stores have those pickled eggs. And that actually came with the shell on it. They did not hard boil that egg and stick it in there. What they did is they just put the eggs with the shell in there and put it in vinegar in there. The vinegar softens the shell and it interacts with the egg inside and pickles it to make it hard. So it will essentially do the same thing to the corals and to some of the other fish in there. So one of the ways they've been able to study this is looking at volcanic vents in the ocean. When you look at the sea life in the coral that is downstream from where those volcanic events are, they notice that there is a definite change in the sea life in those areas. So that is the end of chapter 3.